Hey everybody, we're starting Module 2 today, so we're going to jump right into it, get this going as fast as we can. So Module 2 is on ecosystems, environmental health, and interactions. And as we go through this, there is your learning objectives. You can also find them on the Canvas website. And the title of today's notes is Biochemical Cycles and Energy Flow. It's not too long of a set of notes. We'll try to get through it as fast as possible so that you guys can work on the assignments. So for the introduction, there's a couple slides here just to kind of introduce the topic. In this lesson, we're going to basically explore how nutrients and molecules cycle through an ecosystem, and we'll also learn about how energy flows through an ecosystem. So there's a big distinction between the cycling and flowing. Atoms like carbon, oxygen, nitrogen, hydrogen, and other molecules like water are recycled and converted into many different molecules as they kind of go through and cycle back around. Energy, on the other hand, flows in one direction, and we're going to see that in a little bit. So just for an example of the cycling, we can look at the carbon cycle. So if you take a look at this picture, you see this overall kind of large cycle that's going on, circling around in the carbon cycle. But you also have these little mini cycles where you kind of got some small cycles going on in these little corners and in different areas, kind of picking up carbon dioxide and cycling it through. Some of these cycles are actually very long cycles. They take a long period of time. For example, we're talking about certain carbon molecules that are found in carbon or fossil fuels. They could be buried in the earth for millions of years before they're recycled and put back into the atmosphere. Other cycles might be really quick. For example, you might have the exchange of gas between plants and animals. Animals release carbon dioxide when they exhale, and then the plants kind of pick that up and convert it back to oxygen and release that. So some cycles might be a matter of days, while other cycles could be, like I said, millions of years. So energy, on the other hand, is not recycled. It just flows through an ecosystem, and it moves pretty much in one direction. It's going from the sun, and it is converted to chemical energy by producers like plants. And then that chemical energy is used for growth and development. And then sometimes it gets eaten by another animal, an herbivore, for example, and that energy is transferred into that animal, and that could be transferred into another animal, etc. Eventually, though, the energy kind of dissipates. You got to remember, we're going to see later in the notes that about 90% of the energy as we move from one organism to another organism is lost, either in materials that can't be digested, or it's already used up before it's passed on to the next animal in the form of maintaining a constant body temperature, or could be lost in the form of energy to move around by one animal before it gets eaten by another, and so on. So there's four major systems or spheres that make up the Earth, and we're gonna look at this. There's three of them on here, and then there's the fourth one on the next page. It just wouldn't fit. So there's four major systems. There's the geosphere, the atmosphere, the hydrosphere, and on the next page you're going to see the biosphere. The geosphere is made up of the Earth's core, mantle, and crust. It's kind of like the rock cycle. It's all the different things: rocks, soil, that type of stuff. Atmosphere is going to be all the molecules that are in the Earth's atmosphere, right? It's going to be the air. So it's going to be oxygen, carbon dioxide, atmospheric nitrogen, that type of stuff. And then the hydrosphere is going to be the solid, liquid, and gaseous water that we find on the Earth. And the oceans are going to make up about 97% of the hydrosphere, and the remaining 3% will be in freshwater lakes and rivers and glaciers, as well as atmospheric water that's in the form of water vapor and that type of stuff. And then finally, we have the biosphere. This is a collection of all the Earth's life forms. Now, we've already kind of talked a little bit about the biosphere in Module 1. So you're going to see that in ecosystems, when we're studying ecology, going through these various modules on ecology, there's going to be a lot of overlap. So what we talked about in Module 1 will come up in Module 2, and what we talk about here in Module 2 may come up in Module 3, and it's going to kind of all be interlinked. So this includes all of the biomes: tundra, boreal forests, temperate forests, temperate grasslands, deserts, savanna, rainforest, chaparral, the aquatic ecosystems like fresh and marine ecosystems, and those type of things. So these four spheres are all connected in various ways. So you're going to see a lot of interconnection in ecology. I'm going to give you three quick examples using a volcano. And don't get caught up in memorizing these examples. This is just kind of showing you a few examples on how this is all tied together. So if we take a look at the first one, let's say we have a volcanic event, right? An event in the geosphere, a volcano erupting, releases a large amount of particulate matter into the atmosphere. So now we have the atmosphere being affected as well. These particles serve as the nuclei in the formation of water. So now we're dealing with a hydrosphere. Then the rain would fall back to Earth. This is back to the hydrosphere again and often increases following an eruption, stimulating plant growth. Now we're affecting the biosphere. The particulate matter in the air, which is in the atmosphere, may fall out and initially smother the plants, dealing with the biosphere again, but ultimately enriching the soil, which is part of the geosphere, and thereby stimulating plant growth back to the biosphere. That's one example. Let's look at another one. We have a volcano that erupts, right? It may release a substantial amount of hot lava. That's affecting the geosphere, the rock cycle, which causes mountain glaciers to melt. That would be the hydrosphere. Mud flows could occur with the flooding. That would be the geosphere again. And then that could lead downstream from the volcano and may actually inundate streamside communities, which would be the biosphere. And let's look at one more quick one. And again, try not to get too confused. This is just a demonstration that show how all this stuff is kind of interlinked. A volcanic eruption occurs and may emit large quantities of sulfur dioxide into the atmosphere. So we're going from the geosphere to the atmosphere. When the atmospheric sulfur dioxide combines with water, it becomes sulfuric acid, right? So now we're dealing with the hydrosphere. When that rain falls back to the earth, the hydrosphere is affecting the geosphere again. Lakes and rivers can be affected. That's back to the hydrosphere. Acidic waters leach nutrients from the soil, the geosphere, into the water table, back to the hydrosphere, making soil less fertile for plants, which is back to the biosphere. Then the subterranean water supply, the hydrosphere, less potable for humans, which is the part of the biosphere. And then you have acid rain that could be filling lakes, streams, reducing the pH of the water, affecting the hydrosphere again, which may result in a decrease in phytoplankton and zooplankton, which would affect the biosphere. If the photosynthesis is reduced, atmospheric concentrations of carbon dioxide can build up and stimulate global warming. Now we're back to the atmosphere, which may also contribute to increased melting of glaciers, which is the hydrosphere. So when we're looking at this, you can see there's a lot of interlinking, and that can affect all those four levels, right? Hydrosphere, geosphere, atmosphere, biosphere. But what we want to do now is move on to the second part of this, which is going to focus on the trophic levels. The feeding position in a food chain or food web are called trophic levels. All food chains and webs have at least 2 or 3 trophic levels. Usually you don't go too much further than 4 or 5 levels, and you'll see why in a moment. Many consumers feed at more than one trophic level. Lizards, for example, in this picture, would be feeding off the plants, which would make them primary consumers, herbivores, right? But they're also eating insects and smaller lizards. So they're eating at multiple levels, or they're secondary consumers in those regards. So the table in Canvas will show the trophic levels and where the organism kind of gets their food in an example from a desert food web. So make sure you look at the table in Canvas, and it's right next to the exact same picture that's in Canvas as well. So you may have seen the pyramid diagrams like the one off to the right in ecology before. This is because they're a great representation of the different aspects of an ecosystem. The pyramid illustrates that the top trophic level increases from the producer level, which is way at the bottom, to the quaternary consumer level. And as this goes up, you'll notice that it's really wide at the bottom. That shows a large biomass and lots of available energy. And then it gets more narrow at the top, which is less biomass and less available energy. So in addition, it can also be useful to show a decrease in the available energy and the biomass that you have as you move up these trophic levels. Energy is passed up a food chain or web from lower to higher trophic levels. However, generally only about 10% of the energy is going to make it from one level to the next. This loss of energy explains why there's rarely more than 4 or 5 levels in a food chain or food web. Sometimes there may be a 5th level, but usually there's not enough energy to support any additional levels past that. Occasionally you might get more levels in aquatic ecosystems because they're a little bit more stable, but usually you're right around 4, right? So with less energy at higher trophic levels, there's usually fewer organisms as well. Organisms tend to be larger in size, but less in number, so a decrease in biomass at those top levels. And biomass is basically the total mass of organisms in a trophic level. So you may have millions of producers in a particular ecosystem and only maybe thousands of consumers and maybe only hundreds of secondary consumers and maybe even dozens of tertiary consumers and then maybe only one or two of these quaternary consumers in a particular area. So how does this energy flow? Well, the sun supports most of Earth's ecosystems. There are a few exceptions like way at the bottom of oceans near underwater volcanoes, thermal vents, where organisms are feeding off of inorganic molecules like phosphorus pouring out, or sulfur pouring out of underwater volcanoes and stuff like that. Because it is the ultimate source of all energy on Earth, plants are considered producers and they kind of absorb the sun's energy and convert it into chemical energy. So plants create chemical energy from abiotic factors that include the sun's energy. And then, as I mentioned, you have chemosynthesizing bacteria that could create usable chemical energy from unusable chemical energy like sulfur and stuff like that at those unusual places at the bottom of the ocean. The food energy created by producers is then passed on to consumers, scavengers, and decomposers. Most of the energy at a trophic level, about 90%, is used at that level. The organisms need it for growth, locomotions, heating themselves, reproduction, new cell development, whatever. So animals at the secondary trophic level only get about 10% as much energy from, or 10% of the energy available at the first trophic level. And as do organisms at the first trophic level, giving it off to the second trophic level, and then the third trophic level. So there's a loss of 90% of the energy every time we go up a trophic level, which is one of the reasons why you don't see food chains that are much more than 4 or 5 organisms long. There's just not enough available energy. As a matter of fact, if I go back to this pyramid, if you think about this pyramid, it's actually a misrepresentation. It's a good graphical representation to understand this. But if we were going to make this more accurate, the pyramid would be nearly flat, right? It would be at a much shallower angle. So we would see that when we're at one trophic level, right down here, you'd have a big drop off because only 10% would be passed on to the next trophic level and so on, okay? If you were thinking of it as in terms of energy. So since that's the case, since that's a little bit of a misrepresentation, right, we're going to look at another quick pyramid. It's the exact same pyramid, except this has percentages written in. Since we can't draw it very well on the pyramid, we're just going to write the percentages in. So as you can see in the image at the right, you also move up the pyramid, the amount of energy is decreased. This decrease in available energy is why each level above has fewer organisms than the level below it on the pyramid. There's not enough energy to support more organisms in the 5th or 6th trophic level, and then again in some ocean food chains you might have 6 or so levels, but that's because it's a little bit more stable than land ecosystems. So if we look at these percentages, if 100% of the available energy were captured by producers, you'd have tons of producers, but only a small percentage of the sun's energy is actually captured. So this 100% actually represents how much energy is available within the producers themselves, the grasses, the plants, whatever's capturing the sun's energy and producing food or producing chemical energy. So when one of these is eaten by a primary consumer, only 10% of that available energy is passed on to this level. And then if we decrease that again, now we're down to 1% of this overall 100% that was down here at the second consumer level. At the third level, it's 0.1%, and then at the apex predator, it's about 0.01%, which is why you don't have very many more levels in these energy pyramids than 3 or 4 or 5. So where does this energy eventually go? At each level of the food chain, a lot of the energy is lost, right? Only about 10% of the energy is passed on to the next level, as we said. So where is this energy going? Most of the energy is given off as heat. It's lost to the atmosphere. It's lost to the environment, right? Some energy goes into the animal waste. Think about it. If you eat something, it's not 100% conversion. You don't get energy from 100% of the food. There's some waste product. If there was no waste product, you'd never have to go to the bathroom. So energy also goes into growing things that the consumer can't eat. So fur, bones, the stuff that can't be consumed or digested by other animals. That's going to be some of the energy is going to be lost in that, making those materials. And then another portion of the energy is used by the organisms just to carry out their daily functions, to be able to get up, move around. That all requires energy. You're burning off energy. So moving around, looking for more food, going to work, getting out of bed in the morning, all requires energy. Again, the majority is lost to the environment as heat, but it's also lost doing these various activities and new cell development, growth, etc. It's because so much energy is lost that most food chains just have a few levels. There's not enough energy for those higher levels. So that kind of takes us to the end here. And I'm just going to kind of go over the assignments. You have to do all the self-checks. I think there's 4 self-checks this time. Remember, those go in as a quiz grade. And remember, you can take them more than once. So if you take one of these self-checks and you get 5 out of 5, well, that's great. If you get 3 out of 5, go back, take it again until you get 5 out of 5 because it's going to boost your overall grade. Watch all the videos. I think there's a couple videos, including this one in this module. And then your 3 assignments, one short one, 1.6. You just have to watch a video and then respond to a writing prompt in module 2, 1.6, assignment 1.6. And then module 2, 1.7 assignment is an assignment on the carbon cycle. So we're using carbon cycle to look at that aspect of these notes. And then 1.8 is an assignment on energy flow, and that kind of takes care of that end in the notes. A quick reminder, remember, this is probably going to be the last week that we have any assignments that are going to count towards this quarter. And then the second half of this module, which goes into lesson 2, will start us off on quarter 2. All right, guys, so thank you, and make sure that you guys get all those lessons done. And once you get those done, don't forget to do any quiz corrections you have to do or anything else for the quarter so that we can finish things up and make sure that we put a nice ribbon on this quarter before it's over.